The Columnar-to-Equiaxed Transition, abbreviated to CET. This is the change from large columnar grains to smaller spherical ones during metal solidification. Metallurgists often see the Columnar-to-Equiaxed transition in castings, but in 3D printing or additive manufacturing, it can be difficult to achieve. And in common titanium alloys like Ti, 6% aluminium, 4% vanadium, it has been sought after like some kind of unobtainable mythical beast. We recently conducted our own experiments on the topic, and what we found when we did achieve the CET in Ti 6.4 didn't behave like it was supposed to.
Let's back up a bit. First, when we talk about the CET in these alloys, we mean the refinement of the titanium beta phase grains that form when the metal initially crystallizes from the liquid. Now, why do we want equiaxed beta grains in additively manufactured Ti 6.4? The main drive for this material is aerospace applications, where the weight, material loss, and energy savings offered by additive manufacturing are worth the technological investment into developing the processes.
Usually, with additive manufacturing, you can print small and complex shaped components or large simple geometries. It's a trade-off. And the bigger your components, the more heat inputs you need to achieve the build rates necessary. Usually, this makes your beta grains bigger and bigger, and you end up with massive columnar grains that can span the entire build height. These columnar grains cause a menagerie of mechanical property issues that I won't get into in this video. The key point is that if we change the columnar grains into small equiaxed ones, the problems go away. Actually, without equiaxed grain structures in additively manufactured Ti 6.4 components, it's unlikely they'll ever get used for safety-critical applications in aircraft.
To achieve the Columnar-to-Equiaxed transition, we need to know why columnar grains form in the first place and how to stop them. Let's consider what's happening at the atomic level during a solidifying or freezing metal. It's easiest to visualize this by imagining a two-dimensional system where the metal is solidifying from left to right with a flat interface, where the temperature increases moving away from the solid-liquid interface, which we call the thermal gradient. Atoms in the liquid attach to the solid at the interface in the crystal structure that has the most desirable arrangement. For titanium, this is the body-centered cubic beta phase. In many alloys, it isn't desirable for alloying elements to squeeze into the solidifying base metal, so some of the alloying elements, the solute, is rejected into the liquid, which we generally call solute partitioning. As the interface of our solidifying alloy moves from left to right, a bow wave of solute builds up in front of it. In most alloys, the solute leads to a higher internal energy in the solid, which tends to reduce the freezing point of the alloy. In the case of our solidifying alloy, the solute buildup in the liquid near the solid-liquid interface lowers the alloy freezing temperature. This is well below the liquid temperature, so there is a huge drive for the solid to crystallize closer to the solid-liquid interface. This temperature difference between the liquid and the freezing temperature is known as the undercooling. Farther from the interface, the solute concentration drops, and eventually the freezing temperature rises to become equal to the liquid temperature. Within this region, both liquid and solid can coexist. We call it the mushy zone. This is generally visualized using a phase diagram, an example of which you can see here. This is a titanium iron phase diagram I've borrowed from Graham, Benson and Jackson. Temperature is plotted on the y-axis, and increasing concentration of iron is plotted going from left to right. We can pick an example alloy composition for now, let's say titanium 5 mass% iron. Above approximately 1650 degrees Celsius, we have liquid. As we cool down, the metal begins to freeze, and we hit the liquid plus solid beta phase region, which is the mushy zone. This region only exists because the iron is rejected from the solidifying titanium. We can actually draw a tie line on the diagram at a particular temperature to calculate the exact composition of the liquid and the solid to show this partitioning of iron in the mushy zone.
Within the mushy zone, an undercooling exists, But even with a large undercooling, solid nucleation is still difficult. This can be made easier if there's something in the melt that the solids can nucleate off of. This occurs because the forming solid needs to create less of an interface with the surrounding liquid, which lowers the overall energy requirement for nucleation.
There is theory to rationalise this with a few physical concepts. To describe how material systems behave, we use Gibbs free energy, which, put simply, tells us what a system wants to do, based on whether there is a net positive or negative change in the Gibbs free energy. For metal solidification, a liquid metal cooled below its melting temperature wants to freeze, which is a negative change in the Gibbs free energy, so there is a driving force for nucleation of the solid. This is often called the solid volume free energy. In the graph here, the free energy is plotted on the y-axis and a solid particle radius on the x-axis for a metal below its freezing temperature. The free volume line shows that with increasing particle size, the net change in free energy becomes more and more negative. However, an interface between the solid and the liquid must be created as the particle grows, which the system would rather not do, and is represented by an initial net increase in free energy for the combined Gibbs line shown on the graph. That is, energy must be supplied to create the interface. You may have seen videos of liquids cooled well below their freezing point that don't actually freeze, and a simple flick of the container initiates spontaneous solidification. The flick supplies kinetic energy to the system that allows interface creation and sets off solid particle nucleation. You'll see from our Gibbs free energy plot that once enough energy is supplied, the particle reaches a size r starred, after which the combined Gibbs free energy has a net negative change, so it is favourable for the solid particle to continue to grow. Mathematically, this is because the solid volume free energy is proportional to the particle radius cubed, and the interface is based on the particle surface that is proportional to the radius squared. This energy barrier to interface creation is what makes nucleation in a pure liquid so difficult. However, if the interface area can be reduced, less energy is required, so nucleation is easier. That is, this leads to a reduction in the Gibbs free energy required to reach the critical solid particle radius r star and promotes nucleation in the liquid. We call this heterogeneous nucleation. This is why nucleation can occur easily on a container wall.
But it doesn't have to be a container. Nucleation can occur off of other solid particles in a metal melt pool, and these can be intentionally added nucleants or accidental ones. For example, in titanium, this can happen if oxygen or nitrogen from the air form particles with the titanium in the melt pool, but the contamination level has to be very high for this to happen. With sufficient nucleants and the right solidification conditions, a Columnar-to-Equiaxed transition can occur in a solidifying alloy.
We see this in castings very often, where the alloy solidifies as a single crystal structure off the crucible. The individual crystal grains grow inwards along the thermal gradient without any further grain nucleation, with each single crystal growing as a single structure towards the centre as columns. However, the solute bow wave in front of each forming crystal grows large enough to produce a columnar-to-equiaxed transition, and the structure changes from columnar to equiaxed grains.
Realistically, there's always some nucleants in the melts to help grain nucleation. However, if they aren't of sufficient size or there isn't sufficient number of them, nucleation becomes difficult. Under these conditions, we have to rely on increasing the undercooling to really create a drive for grain nucleation.
There's two ways we can do this. First, we can increase the speed of the solid-liquid interface, also called the solidification rate or front velocity. Since the solute in the bow wave in the liquid can only diffuse away at a limited speed, a faster moving solidification front causes a larger build-up of solute because it can't move away fast enough. And the more solute, the lower the freezing point of the metal and the larger the undercooling. The second method is to reduce the thermal gradient ahead of the solidification front. That is, keep the liquid cooler farther ahead of the solid-liquid interface. Both of these methods increase the overall difference between the liquid temperature and the freezing temperature, but it's most effective to do both simultaneously. And in castings of many alloying systems, the CET is often helped along by adding nucleants with little negative consequences.
Conversely, additive manufacturing is famous for creating very coarse and columnar grain structures. AM processes use a relatively small heat input compared to the material volumes involved, which results in very fast cooling rates with the heat escaping into the rest of the material that acts like a heat sink. This creates small melt pools when depositing layers of metal and, importantly, very high thermal gradients. Think about it this way. AM melt pools are in the order of millimeters, so the hottest part of the liquid and the outer solid-liquid interface are very close together. And casting spans centimeters to meters, where these 2 points are much farther apart.
Titanium has a further problem though. It just loves solute. It's actually remarkable how reluctant titanium is to forming intermetallic particles with many elements. So, when many titanium alloys solidify, there is next to no solute rejection into the liquid, which means limited undercooling. On top of that, titanium alloys are geared towards aerospace applications, so there is very few contaminants in them, which means next to no nucleants in the liquid either. The result? Massive columnar grains.
The AM research community has spent a lot of time and effort refining the as-solidified beta grain structure with the most common titanium alloy, Ti6-4. And it's especially difficult to get a Columnar-to-Equiaxed transition in this alloy because the main alloying elements, aluminium and vanadium, don't partition during solidification at all, really. Usually, Ti6-4 contains a very small amount of iron as a contaminant, and that does partition. But there isn't enough iron in the alloy to really create meaningful undercooling.
The most effective method I've seen to achieve an equiaxed microstructure in Ti6-4 is to use large titanium nitride nucleant particles, which was demonstrated by Dr. Jacob Kennedy. The image on the left here is a reconstructed beta phase EBSD map of a small test wall. The bottom has no titanium nitrides, the top does. The effect is immediately obvious, I'm sure you'll agree. The nitride particles in the liquid haven't changed the undercooling, they've just made the energy cost for grain nucleation ahead of the solid-liquid interface so low that even a smidge of an undercooling is enough here. The downside is that our microstructure is now full of brittle nitrides, so our alloy ductility and damage tolerance drop below the specification required for most applications. Not ideal.
Another method for creating equiaxed grains in titanium is to increase your undercooling by adding one of the elements that does partition enough, as Welk colleagues at Ohio State University demonstrated beautifully. They added up to 6 weight% nickel to Ti6-4, which exhibited remarkable refinement of the grain structure. In the same paper, they also demonstrated a similar grain refinement effect with high iron levels in a similar two-phase titanium alloy, strongly suggesting iron could be used to achieve the CET in Ti6-4. Here's the problem though. If you're looking to produce Ti6-4 with an equiaxed grain structure for an industry application, you can't add a significant amount of another alloying element without needing to completely requalify or even redesign the application around it. It's unfortunate, but it's the reality. For aerospace applications, qualification of a new alloy can take several years. There are many such examples of adding large concentrations for extra alloying elements to Ti6-4 to achieve a Columnar-to-Equiaxed transition, but these aren't Ti6-4 anymore by definition. Ideally, we'd like to achieve a CET without alloy modification. The last trick to refine your beta grain structure, keeping your alloy the same, is to change your AM deposition process to change your solidification conditions. That's your thermal gradient and your solidification rate.
In the pioneering work by Cobrin and Semiatin, a variety of casting and AM methods were used to produce Ti6-4 samples with varying thermal gradients and solidification rates. The samples exhibited columnar grain structures, equiaxed and a mix of both, allowing a CET guide map to be constructed. These are commonly called Hunt maps, as the solidification conditions required to produce columnar or equiaxed grains in metals were first modelled by J.D. Hunt in his 1983 paper on the topic, and are shown on Cobrin and Semiatin's CET map as the solid and dashed black lines. Our research team decided to look into this grain refinement method in more detail, specifically investigating the realms of possibility with high-deposition-rate directed energy deposition AM processes like wire arc AM or WAM, which are of high interest to aerospace industries.
The first step was to use the models and previous research available to establish the theoretical bounds of what was possible with Ti-6-4 through solidification manipulation. This was done by Dr. Daniel Dreelan. I'll skip the model details. You can find more information in our published paper, which is in the video description. But in short, we estimated the undercooling caused by solute rejection at the tip of a dendrite crystallizing in Ti-6-4 using the KGT model, then produced CET maps of the change in thermal gradient versus the solidification rate using Hunt's approach. First, let's look at the predicted dendrite tip undercooling.
This plot shows the undercooling as a function of the solidification rate in millimeters per second up to 20, which is equivalent to the melt pool movement speed and is the practical limit for most directed energy deposition AM processes. We made sure to include standard alloy limits of iron contamination in Ti-6-4, since iron partitions the most strongly during solidification in this alloy. Within the solidification rate range, you can see the standard alloy limits for iron produces a very low undercooling, about 2 Kelvin. But this now poses a question for us. How much undercooling do we actually need to achieve for a CET in Ti-6-4? Fortunately, Welk and colleagues gave us a calibration point of sorts. Their work using increased levels of iron in a similar two-phase alloy to Ti-6-4 showed us that about 2.7 weight% iron is needed before the CET begins. If we run our model for this iron level in the solidification rate range, we can work out that an undercooling of approximately 8 Kelvin or more is needed to achieve the CET, which the standard Ti-6-4 doesn't even come close to.
However, we haven't considered nucleants in the melts. Unfortunately, we can't ascertain what the number of nucleation sites were in the melts for the titanium high iron example. However, using the provided Hunt map, we can use Cobrin and Semiatin's work to glean some information on this nucleation site density.
If we plot our model using standard Ti-6-4 for a variety of undercoolings and nucleation site densities on Hunt maps, which include the columnar and equiaxed condition boundaries, we can see that the best fit to Cobrin and Semiatin's data is a nucleation site density of 5 × 10 to the power of 14 sites per meter cubed, and an undercooling of 1.1 Kelvin, which approximately matches our initial undercooling estimate shown before. This suggests that Cobrin and Semiatin's work had a relatively high number of effective nucleants in the melt, which we know from comparison of other literature that suggests site densities in the range of 5 × 10 to the power of 7 to 2 × 10 to the power of 9, which achieved equiaxed grain structures with undercoolings of 4 to 10 Kelvin.
So, what does this mean for directed energy deposition AM processes like WAM? When building aerospace parts, limiting contamination is extremely important to stay within the required material specifications, so samples are usually deposited using an argon shielding gas to prevent oxygen and nitrogen entering the melt pool. And even if some of these contaminant gases did enter the liquid metal, existing theory suggests that very large 500 nanometer nucleant particles are required to be effective at low undercoolings like 1 to 2 Kelvin.
As was shown in Kennedy's work with the titanium nitride particle additions, and seemed highly unlikely to form under WAM deposition. However, for an undercooling as high as 8 Kelvin, like in the titanium high iron example, nucleants a fifth of the size are likely to be sufficient, which are far more likely to be present.
So, if we want to avoid Ti-6-4 alloy modifications and achieve the CET in these processes, we're stuck with altering the AM process we're using to manipulate our thermal gradient for increased undercooling, as no other approach would appear to be feasible within stable AM processing windows.
One such approach was demonstrated by Dr. Wang and colleagues at Cranfield University. Their approach was to increase the wire feed speed during WAM deposition, while keeping the heat input and travel speed of the melt pool the same. Due to the larger volume of material to melt, this would theoretically cool down the melt pool and reduce the thermal gradient at the solid-liquid interface. By progressively increasing the wire feed speed from 27 to over 37 millimeters per second while depositing a single bead Ti-6-4 WAM test wall, Wang and colleagues demonstrated a somewhat successful CET. This shows us that this approach works to some extent, but not why.
Our team decided to investigate. At Cranfield University, Dr. James Wainwright deposited a series of Ti-6-4 test walls with increasing wire feed speeds under otherwise identical processing conditions. James also printed Ti-6242 alloy samples. This is an alloy similar to Ti-6-4 that has a slightly larger mushy zone during solidification and so would provide altered solidification conditions to compare to in the study. Also at Cranfield University, Dr. Chen carried out computational fluid dynamics simulations of the same depositions to investigate the effects of increasing wire feed speed on the thermal gradient and solidification rates in the melt pools. Professor Phil Prangnell and I then carried out the microstructure characterization and metallurgical analysis to piece the whole picture together.
These EBSD maps show the beta grain structure of the samples, which have been reconstructed from the alpha phase data. In this cross-section, the WAM build direction goes from bottom to top, and the heat source travels from left to right. At a wire feed speed of 27 millimeters per second, the grain structure was overwhelmingly columnar, with only a few small equiaxed island grains, which are arrowed in the top image. The grains appear red in this colour scheme, which indicates the strong texture that the grains form with. When the wire feed speed hits 47 millimeters per second, there is an abrupt change to an equiaxed structure. With a further increase to 50 millimeters per second, however, there is an odd transition that elongates the grains in a heat source travel direction. This grain aspect ratio change is accompanied by an increase in size. Both effects are also seen in the Ti-6242 samples. Now, if our theory was correct, and the progressive increase in wire feed speed continually reduced the thermal gradient, more and more nucleant particles in the liquid would tend to nucleate grains, and our grain size would continue to decrease, not increase after a certain point. So, this observation doesn't fit with CET theory.
We found something else weird too. If grains were nucleating in the liquid during WAM deposition off of particles tumbling around in the melt pool, we would expect their relative orientations to one another to be random, as they were in Kennedy's work with Ti-nitride nucleants.
Here are the misorientation profiles of the grains from the reconstructed beta phase EBSD maps. For the low wire feed speeds and columnar structures, which are the black and red lines, there are low misorientation peaks that represent the relative orientations of the columnar grains. For the 47 millimeter per second wire feed speed, the low misorientation peaks radically reduce and new peaks appear, most prominently at around 60 degrees. Phil and I had seen this misorientation peak before. It relates to twinning in the titanium beta phase. This was a truly bizarre discovery for us.
Clearly, something else is going on that doesn't abide by conventional CET theory, but let's start there anyway. Increasing the wire feed speed was supposed to lower the thermal gradient in the melt pool, create more undercooling, and activate the CET. This is what Shin's simulations were supposed to prove, but they didn't. Not really.
Instead of predicting a significant decrease in the thermal gradient when trying to deposit a higher volume of wire, what we found instead is that the process self-compensates for the higher wire feed speed. Usually with WAM, we use a large remelt depth of the substrate when depositing wire layers to avoid defects. If you increase the wire feed speed, the heat energy is effectively redistributed from the remelt to the larger volume of material you're trying to melt. This leads to only a small reduction in the thermal gradient. If we plot this on a Hunt map, our Ti-64 samples with columnar, mixed and equiaxed grain structures are all above the predicted columnar line, demonstrating a breakdown of the CET theory. Back to the twins. We found this 60-degree peak in the misorientation profile that told us there's a strong possibility of twinned grains in our sample microstructures. If we look specifically for the grain-to-grain rotations around specific crystal directions relating to titanium beta phase twin boundaries in our EBSD maps, we see them appearing between many of our equiaxed grains. But these don't look like traditional twins. In fact, they just look like regular grains. Also, twins more often form during deformation or during annealing heat treatments. However, it is possible for twin structures to form during solidification. They're known as dendrite twins, but this can perhaps be a little misleading.
Usually, when a metal freezes, atoms from the liquid attach to the growing solid dendrite in a regular crystal structure. However, atoms can attach in other arrangements to form stacking faults.
Should this stacking fault then grow out into a new grain, a dendrite twin has formed. Should the solidification conditions promote the formation of these stacking faults more regularly, there would be a constant disruption of growing dendrites in the liquid, and each stacking fault-induced grain would continue to grow into equiaxed grains, presenting no visual evidence they ever existed in the completely solidified metal at room temperature. However, since these stacking faults would tend to form with lower energy atomic arrangements, a few types of stacking faults would dominate, which maintain regular orientation relationships to the parent dendrites they formed from, which happen to be the same as those for regular twinning in beta titanium. And these are the twin orientations we're suggesting we've detected between the equiaxed beta grains in the EBSD maps. This would explain why our Hunt maps are wrong. The solidification theory Hunt used for the columnar and equiaxed conditions just isn't relevant anymore. The next question to answer is, why does increasing the wire feed speed during WAM deposition with Ti-64 promote dendrite twinning? The simulations of our Ti-64 WAM samples with high wire feed speeds showed that the heat source remelts less of the substrate to compensate for the large volume of material being deposited. You'll notice that the higher wire feed speed increases the deposited layer height, which you can also see in the optical images of the samples.
It makes sense though. The extra metal has to go somewhere, right? A consequence of this is that the back of the melt pool becomes progressively steeper with higher wire feed speeds and changes the direction of the maximum thermal gradient in the melt pool.
If you have a very shallow melt pool, we know intuitively that liquid metal solidifies from bottom to top. The maximum thermal gradient here points upwards, probably with a slight tilt towards the heat source moving overhead. With a steep back of the melt pool, the maximum thermal gradient at the bottom of the melt pool points upwards again, but at the back, it points progressively more horizontally towards the moving heat source with increasing wire feed speed. The arrows on the simulation images shown here demonstrate this.
The reason we care about the maximum thermal gradient is because the solidifying dendrites grow most quickly in that direction in the 001 crystal orientation for beta titanium, and if you have sufficient rotation of this direction away from the growth direction of the columnar grains, you end up generating new grains. Grains from dendrite twinning, apparently. And we've actually seen this behaviour before, but couldn't explain it until now.
These are beta phase EBSD maps of two titanium alloys, Ti6242 and Ti5553, built with WAM using low wire feed speeds. Both of these alloys have larger mushy zones during solidification. That is, the region where solid and liquid coexist during freezing is larger than in Ti64. The map on the far right is Ti5553, built on top of Ti64 with the same WAM processing conditions. You'll notice that the Ti6042 and Ti5553 both have an outer layer of refined beta grains, whereas the Ti64 doesn't. And here's a Ti6042 sample from the current study where we've investigated their origin more closely. The two example grains, labelled G1 and G2, both exhibit beta twin boundaries. If we compare their locations to an optical image of the same sample etched, we can see they coincide with the boundary between two deposited layers, which curves towards the outer edge of the wall. We can also see that the crystal 001 direction, in which the dendrites solidify, is approximately perpendicular to this boundary, tilted slightly towards the heat source travel direction, which would match the maximum thermal gradient. So, this would indicate that the curved outer edge of the melt pool, where the maximum thermal gradient tilts far away from the vertical alignment of the interior columnar grains, has generated dendrite twins that have grown into equiaxed grains in this outer refined layer. Alloys with a larger mushy zone would allow the dendrite twins to grow longer, which increases the chances of their survival, which is why we don't see this outer layer of refined grains in Ti64, which has a narrow mushy zone. The melt pool in the centre region of all the walls built with low wire feed speeds would be shallow, with a maximum thermal gradient pointing upwards, so columnar grains are expected to dominate here. All of this same theory can be applied to Ti64 built with increasing wire feed speeds. Here's a schematic explaining what we think is going on. With a low wire feed speed, our melt pool is shallow and the thermal gradient more or less points straight up throughout. This allows unobstructed growth of columnar grains from below during deposition of a new layer. With a medium wire feed speed, the back top of the melt pool becomes steeper and dendrite twinned grains begin to form. However, there is still a lot of remelt of the substrates during deposition of the next wire layer, so these grains are remelted back and the bulk consists of columnar grains still. Finally, with a high wire feed speed, the back of the melt pool is tall enough to create constant competition with grains formed at the bottom of the melt pool, so we end up with a mix of equiaxed grains with a variety of orientations, cutting off all columnar growth and producing a weak texture across the bulk, all formed by beta crystals twinning backwards and forwards relative to the maximum thermal gradient.
We decided to see if we could push this mechanism further. If we reduce the travel speed of the melt pool from 4 to 3 millimeters per second, this would further increase the layer height and should separate out the nucleation by dendrite twins at the back of the melt pool and that related to the bottom of the melt pool. We could not have been happier with the result.
In this EBSD map, you can see, especially in the bottom half of the map, horizontal columnar grains, where grains at the back of the melt pool gain such an advantage over the vertical columnar grains that they are cut off in a series of bands. And we show this as a schematic like this.
So we've successfully 3D printed Ti64 with an equiaxed grain structure using WAM without altering the alloy composition whatsoever. Of this testable set, the only downside we found to this technique was the increased curvature of the outer wall layers due to the increased layer height.
This would require more machining than a lower wire feed speed wall with a flatter edge. Not a big deal, I think, personally. However, I have to recognise that we will face challenges printing actual components with more complicated shapes than just simple single wire bead walls.
In terms of the dendrite twinning theory, I think it definitely has merit. No, we haven't proved it conclusively, but it fits all the evidence and observed metallurgical behaviour found in this study, and no other current CET ideas fit well. Please do have a read of our paper published on this work, which there is a link to in the description of this video, and if anyone has a better idea of what's going on, please let me know.